Hello everyone, let's get started again. In this video, we are going to discuss our continuation of the deformation gradient. In the previous video, we stopped at this point, right? So that means we define what is deformation gradient. What is actually deformation gradient? We measure change of a line vector in current configuration with respect to the reference configuration, right? Okay, so here I have drawn this diagram, right? So what is this actually? Okay, so this is again the current configuration. This is the reference configuration. Okay, so this is current configuration, right? Okay. In reference configuration, this is our line vector, one point the position vector. This is the change in that line vector in current configuration. That means cabal X here. Similarly, in current configuration, the change in that vector, this position vector now, it is d small x vector, right? Okay. So now this one, as we defined earlier, that is u vector. So therefore, this is because of the increment of these two. This will be u plus du now. Okay. The same diagram I have drawn again, right? Because if I mark everything here, this diagram will be meshy, right? Okay. Right. So now I'm going to define a lot, right? So what we have discussed already, this one already we discussed, right? Okay. If I write it this one in index notation, how can you write? D, this vector, I need one pre-index here. This side, the same pre-index must be adapted, right? Okay, so therefore, I will put f here, dx here. You remember the multiplication rule for index notation. That means when you multiply second order tensor and the vector, the second subscript of the tensor must be same as subscript of the vectors. Therefore, if I put here, because it is current configuration, I'll put capital K. So here the same K must be for the second subscript here, right? So because of left side we have I is a free index, same free index must be adapted here. Okay, so this is your equation number one, right? Now let's discuss this one. So now here I have represent the current configuration change with respect to the reference configuration one, right? The same thing if I want to represent the reference configuration 1 with respect to current configuration, if I follow the index notation, so here I have to write a matrix, right? I will put F here. Here what I have to do, that means repeated index is similar to the previous case. Here I will write it uh, I here, I small I, and the same free index this side, capital K here, right? So this is your equation number 2, right? So what is the second equation? What I have done here, I represent the reference configuration change with respect to current configuration, right? Okay. So from equation number 1, if I consider the vector form, that is the first one, right? This one. Okay, dx. From here, if I want to find dx vector, I have to re-multiply with f inverse, right? So therefore, f inverse here, the right side f is inverse into f, that is identity matrix into dx, same dx, right? So this is dx vector. Okay, this is actually the second equation number 2 in the matrix form. So therefore, what you can write the your F inverse actually Fki, right? Okay, right? F inverse is Fki. So this is something you must know, right? Okay. So what is actually this one, right? F into F inverse, it's identity matrix, right? So the same thing you can write it here. What is your F? F actually we discussed already. If I came in this one, right? Right? This is your Fik, right? So that means F mean dou current configuration 1 into reference configuration K. Okay, right. So what is Fki? Then how can I write Fki? So first one for capital, that means reference configuration, and second one is a small. The first one is a capital K, right? Therefore, this one. Second one is a small I, therefore current configuration small x, right? Okay. Finally I have to get identity matrix. Therefore, I cannot use I because both repeated index here. I will use different one. Why? So because of second order tensor, I should get two free index, right? So I and j, kk is repeated index, right? So this is your inverse F matrix. Okay. So this is your inverse matrix, right? So this actually delta ij. It's same, right? Because these two cancel out, you will get this one, right? This already we discussed delta ij or ji, right? Both is same. Okay. Okay, I hope this point is clear, right? Okay, this diagram, I need this one, therefore I kept it here. Okay, let's discuss some of the important stuffs here, right? Um, we discussed this one. Okay, right. Okay, so from the previous equation, F inverse is exists, right? So that means if inverse is exists, that means this is invertible, right? So therefore, it should be non-singular. Therefore, determinant of F shouldn't be 0. This is a very first point you must know, right? So that means what is F actually? F is related, right? F we can write F I K, right? And this is related um, two coordinates, right? Two coordinates. Okay. So what are the two coordinate? Material coordinate, Lagrangian and Euler, right? Material and spatial, right? So these two coordinate, it's connecting, combining both, right? Then um, because of that, sometimes this some books they call this one as 2-point vector, right? 2 point 2 point not vector tensor, right? 2-point tensor. Okay. Okay. Then uh, it's again it is a linear operator, right? Because it is why it is linear operator, it's connecting the line, right? It is a linear operator. It's a linear operator operator which relates relates every line. Okay. uh, every I will write material line, right? Instead of material line, every material line, right? So that means material point, right? So material line uh, to spatial line, right? Material line, line element, right? Line element dx, right? Dx in reference configuration we have taken as B, right? In B uh, to the uh, to the corresponding, right? Corresponding dx, right? In B, right? Reference configuration, right? So this is we have taken as capital B and small b, right? So every line here, whatever the line, if you take 2 points here in current reference configuration, it connect in the current configuration one. This is your F, right? Okay. This is one important thing. Next one, just now we discuss, it is not zero, right? Deformation gradient is not zero. So that means deformation gradient is not zero. This one is not zero, mean this one, right? So that means determinant of F. So it is actually this one, right? dx over x, right? So this is not equal 0, right? So this is we are calling as one of the axiom in continuum mechanics, right? Okay. So because this is not 0, right? This is very important. You must know. Okay. Right. Then the uh, the current configuration, right? The current configuration you can represent in terms of reference configuration coordinate, right? Function. Because current configuration, you can represent that current configuration coordinate point with respect to the reference configuration one, right? So this one you can convert into, right? So let's say current configuration. So current configuration with respect function of reference configuration point and time, or reference configuration one, current configuration and time, right? So these two inversion, right? One is forward, a backward. Then both we are doing with this one, right? The forward you are using F, the backward you are using F inverse, right? So this relationship we discuss, right? That is what we call this is invertible. This is one thing, right? So another one is also very important. This determinant of F, it is we consider greater than 0, not equal 0. Why we consider greater than 0? This is very important point, right? Why we consider greater than 0? Because if it is greater than 0, what is happening actually? So that means this point, it is actually increasing, right? The point is increasing. If you ask me in the real case, the deformation continuum mechanism, always the point is increased, right? That means volume of the material increase. Okay. You can ask me, okay, if you apply compression force, volume is increased. Yeah, there are only two possibilities. Volume, one is it will be constant or increase. So never it's reduce unless if you take the material out. Why I'm saying you studied something called Poisson ratio, right? When you apply this way, vertical direction, the lateral direction is expand, right? That is something called Poisson ratio. No? Based on the Poisson ratio, you see one is material incompressible, volume constant or increase, right? So therefore, always this must be remembered, right? So why we keep this one? This is something you know, right? So why we keep one? This is called physically uh, a realizable deformation, right? Or admissible deformation, right? Physically realizable deformation. Okay, right? Or in other word, admissible deformation. Okay, if you ask me, can't we consider deformation less than zero? There are situations, right? Uh, okay, I don't want to confuse you bringing that idea here. Okay, I will tell you lightly. For example, if we want to model in finite element, if we want to model something, let's say one material you are going to cut, remove from another using the some that simulation, right? Let's say sizzle and the wood. If you are removing this one, if you want to model that one in the finite element, actually we capture that removing part using less than zero, because in that case the volume is reducing, right? Okay, so we consider that one also, but in continuum mechanics we don't consider that one, right? That is for finite element, right? Okay, right. So now in this picture, what I'm going to do now, uh, okay, let me stop at this point, right? I'll start at new page, right? I have told everything, I think. Mm, okay, before that, right? Before that, let me bring, okay, before stopping this video, let me bring this one into next page. Okay, 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 keep this one. Okay, let me bring one more thing, right? Okay, so here, okay, if I show you this diagram, you'll understand. Now you can connect this x and u in using the vector addition notation, right? X plus u is equal small x, right? Okay. Okay. So what is this one actually? You have one vector like this, right? So that is your one vector is here, that is your capital X, right? So then you have something called u, vector u. So this is your small x vector, right? Okay. So now you can apply the vector addition rule, right? So that means x plus vector u is equal x, right? Okay, this is something you know, right? If you write it in index notation, xi xi plus ui, right? Okay, so why everything is I am using the same pre-index, right? So now if I consider the differentiation of this one with respect to, okay, with respect to reference configuration, right? Okay, L is capital. So this one xi, xk, both are now reference configuration. This one dui do xk. Okay, right. So this is actually your f, right? F I k equal, right? Okay, this is actually your f, right? F I k equal this one, both are in same coordinate system. Therefore, this is delta I k plus. So this one, your displacement gradient, right? That means u I comma k is something we discussed already, right? So this is your displacement gradient, right? So this is called displacement gradient. Okay, the previous one, f is a deformation gradient, right? If you consider in a matrix form, this is equal identity matrix into this one. It is actually a deformation gradient, right? So that means we will write like this, right? Okay, right. You know what is the meaning of this one, right? This is actually the vector, right? So this is, we discussed something called gradient, right? Okay, so this is also one of the important relationship between deformation gradient and displacement gradient, right? Okay. Okay, so let me stop at this point. If you have any questions, please let me know in the comment section. If you do not subscribe my channel, please subscribe. Also like the video and share with others, right? So see you in next video, right?